This lesson is designed to teach you about how fractional numbers are represented in binary in general. In an earlier lesson, I explained how you can represent any whole number as a binary number. We also developed a system that allowed us to do this for negative numbers using a sign bit. Therefore, as far as integers are concerned, you can represent any integer value as a binary number. However, what happens when you have a number like 2.5? How can you store a number like this in binary? Well, first of all, how do we do this in base 10? And of course, base 10 is decimal. That's the numbering system that we're all used to. So, in decimal, how do you represent fractional parts? Well, you cut the number into two parts. The left-hand side of the number is an integer, and then you put a period, and then you put the fractional part. Let's look at this in detail. So here we have the number 172, and we are defining a fractional part as 31 hundredths. If we looked at this according to what we have learned about place values, we see this. There is a 1 in the hundredths place, there is a 7 in the tens place, there is a 2 in the ones place, and now there's a 3 in the tenths place and a 1 in the hundredths place. So in base 10, the way it works is we start with tenths, then hundredths, then thousandths, and so on. Now let's look at a different number, but in binary this time. Okay, so the binary number that we're looking at here is right here. Now we know the integer part is 6, because that's the 4's place, that's the 2's place, and 4 and 2 is 6. So what about the part after the decimal? Well, remember that in base 10, you go 10, 100, 1,000, and so on. In binary, you have the exact same concept, except you're doing it in base 2, so you go 2, 4, 8, 16, but as fractional parts. So here is the same number, but I have aligned it under the place values of the different fractional parts. So it should be very easy for you to see that this number is 6.5. Basically, it's the equivalent in decimal of 6.5, because we have a 1 in the half place. So remember, in binary, after the decimal, you have 1 over 2, 1 over 4, 1 over 8, 1 over 16, and if we were to go 1 over, that would be 1 over 32. And that's how you express a fractional number in binary. Now notice I just changed the value. Now instead of it being 0.1000, it's 0.1100. So how does the value change? Now instead of this being 6.5 effectively, or 6.5, it is now the equivalent of 6.5 plus 1/4. So 1/2 and 1/4 is 3/4. So now the number is effectively 6.75, or 6 3/4. Now what about if we had a value like, say, 8.1 in decimal, that is 8 1/10? This becomes a lot trickier, because in binary we are working with 2 as the base. There is no such thing as a tenth. We have to approximate by coming up with as close as possible of a value to 1/10. And here's how we do that. Alright, so remember, these are binary decimal values. So we start with 0.1. Now, that is equivalently 1/2, which is too large, so that won't work. So let's try this binary value, which, if you remember, because this is the half place, then this must be the quarter place, 1/4, which is still too high. So let's try something else. So let's try 1/8. So we have 1/2, 1/4, 1/8. And this is still too high, but it's closer to being 1/10. Now if we were to try 1/16, we're now too low. So it has to be in between 1/8 and 1/16. So if we keep working with this idea, we will eventually find that having a 1 in the 1/16th place and a 1 in the 32nds place will effectively be 3 32nds, which is pretty close to 1/10, but not exactly. Now, if we were to have 3 30ths, we would have exactly 1/10, but since we have 3 32nds, we are close to 1/10, but not quite there. So we would still need to add more and more binary digits to get closer and closer to 1/10. So notice that the more digits that you add, the closer you can get to a particular fractional number. For some numbers, it's possible to reach exactly the value that you want. So for example, if you need the value 1/2, it's very easy to do that. So this brings up a question. If you are going to store this value, which is effectively 6.5 in binary in your computer, and you are only allowed to store ones and zeros in your computer, then how do you store this decimal point, which, by the way, is also called a radix point? How do you do that? The answer is you don't. Instead, you specify the number of bits that will be used for the integer part, which in this case is 4 bits, and you specify the number of bits that will be used to the right of the radix, which is also in this case 4 bits. If you wanted to store the value 6.5 in the computer, all you need to do is store the complete binary value without any decimal point, and then instruct your program to treat the first 4 digits as being part of the whole number and the last 4 digits to be part of the fractional number. And we will get into exactly how this is done in a future lesson. One thing that I want you to see from this lesson is that there is always going to be a limit to how accurately you can store a number, and that limit is always going to be the number of bits you have available to store it. So in our example, when we were trying to obtain the value 1/10, we could only get as close to that value as the number of bits we were allocating. If we wanted to get closer, we would need more and more bits. So always keep this in mind when you are writing a program. The more bits you have available to you, the more accurately you can store a fractional number.